Hello, my name is Kirti. In this lecture, we shall solve 4 numerical problems on Arrhenius equation. So, I had already posted 2 videos on this topic. In the first video, I had covered the theoretical portion, and in the same video, we had derived these 3 different forms of Arrhenius equation. So, before you come to solve the problems on Arrhenius equation, you need to watch that video. I'll give the link in the description, okay? And in the second video, we had covered about 5 problems. So this video is the continuation of the second video. So in this video, we will start solving from problem number 6. So let's begin with question number 6. The question is, the rate constant of a reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. Calculate EA. So you are asked to find the activation energy here, okay? So 2 temperatures are given here. The initial temperature is 298 Kelvin, which I will take as T1, which is 298 Kelvin. The rate constant of a reaction doubles. Let us assume the initial rate constant, which is K1, as K, okay? So what it is given? The rate constant of a reaction doubles for an increase of 10 Kelvin in absolute temperature from 298 Kelvin. So what is the final temperature? Final temperature is 10 Kelvin more than this temperature. Then how much it is? 298 plus 10. That is 308. Okay. So the temperature T2 is 308, and at T2 what happens to the rate constant? It is said that the rate constant of a reaction doubles. So if K1 is K, then K2 at T2 will be 2K, double of K, okay? So this information is given in the question, and now you are asked to calculate the activation energy. How will you do this? So which of these equations can you use? You can clearly see that you can use this equation, K2 by K1, because we have 2 rate constants, 2 temperatures. We have 2 temperatures and 2 rate constants. We need to find activation energy. So this equation is suitable to solve this question. Okay. So what will I do is, I'll just put the values of all those terms, log K2 by K1. So what is K2 here? It is 2K. What is K1? It is K. EA is not known, that we have to find, and denominator is 2.303 R. What is the value of R? 8.314. Okay. So I will also write its unit Joule, Kelvin inverse, mole inverse. Okay. So the unit of R is Joule, Kelvin inverse, and mole inverse. So what is T2? T2 is 308 minus T1 is 298 divided by T1 into T2. That is 298 into 308. So here I can cancel K. So this becomes log 2. Log 2 is 0.3010. So this value is 0.3010. And in the denominator you have 2.303 into 8.314 Joule, Kelvin inverse, mole inverse. And in the numerator, 308 minus 298 is 10. And in the denominator, we have 298 into 308. Okay. So I will keep this EA here, and I will take this entire value on the left hand side. It becomes 0.3010 into 2.303 into 8.314 Joule, Kelvin inverse, mole inverse into 298 into 308. Here it is Kelvin square, because 298 Kelvin into 308 Kelvin, it becomes Kelvin square. And in the denominator, you have 10. So 10 Kelvin. This is also Kelvin minus Kelvin is Kelvin, right? So I'll write the units in the bracket here. This is Kelvin, this is Kelvin square. Now first try to cancel the units. So here I can cancel 1 Kelvin with 1 Kelvin here. So this Kelvin inverse and Kelvin will get cancelled. So when you multiply all these terms and divide it by 10, the answer you get is 52,897 joules. Okay, so this is your answer. If you want to express it in kilojoules, just divide it by 1000 and what you will get is 52.897 kilojoules. So this is your answer. It was simple, right? You were given two different temperatures, two rate constants, and you are asked to find the value of activation energy. Okay. Now let us move to the 7th question. Now let us solve the question number 7. So the question is, observed rate constant of a reaction is given by K observed is equal to K1 into K2 square over K3. Find the expressions for overall frequency factor. So frequency factor is A and activation energy of the reaction. So we are asked to find the value of A and EA for the given reaction. So what is the observed rate constant given here? K observed is equal to K1 into K2 square over K3, right? So by looking at this expression for overall rate constant, what you can say? You can say that this reaction must be a multi-step reaction or a 3-step reaction because it involves 3 rate constants, okay? So there are 3 steps. 1, 2, 3, and in the first step the rate constant is K1, in the second step the rate constant is K2, and in third step it is K3. So each step will also have its own activation energy, right? So in the first step the activation energy is EA1, in second it is EA2, in third it is EA3, okay? And in each step the Arrhenius parameter will also be different, right? So the Arrhenius parameter here will be A1, here A2 and here A3. But the temperature will remain constant because temperature does not change with each step of a reaction, right? It is constant for the entire reaction, okay? So here T is constant. So now we have this information. Now we move on to find the value of overall frequency factor and activation energy. When you look at this equation, you can write this K1 or rate constant in the form of A into e power minus EA over RT. So this is the expression for rate constant, okay? So in the place of K1, I can write K1 as A1 into e power minus EA1 over RT, okay? In the place of K2, I can write A2 into e power minus EA2 over RT, right? And here there is square of K2, okay? So we'll square this term. And in the place of K3, we can write A3 into e power minus EA3 over RT, okay? So how can I solve this? I can bring A1, A2, A3 at one side together. So this is A1. So A2 has a square. So I will write it as A2 square by A3. Now we have e power minus EA1 over RT into, now this is in the form a power n whole power n, right? E power minus EA over RT whole square. So this is in this form. So a power m whole power n becomes a power n into n. Okay, this is basic mathematics. Okay, so here I can write this as e power 2 into minus EA over RT. That becomes minus 2 EA2 over RT. Okay, so in the denominator we have e power minus EA3 over RT. So I'll take it to the numerator. So it becomes E power plus EA3 over RT. So here I will write it as E power EA3 over RT. Okay. Now when the bases are equal, the powers can be added, right? So all the bases are E here. So I will add their powers. What will I get? I will get it as E power minus EA1 over RT plus minus 2EA2 over RT plus EA3 over RT plus EA3 over RT. So I have just added their powers, okay. So A power M, A power N, A power P. So it was of this form and I made it as A power M plus N plus P. So this is what all I did, okay. Okay, now when you look at this equation, so this is of the form K is equal to some constant A into E power minus EA over RT, right? Okay, before that let me write it this way. I can write this term as, so I can take RT common from each term. So I can write it as minus EA1 minus 2EA2 plus EA3 whole divided by RT, right? I'll write it properly. Minus EA1 minus 2EA2 plus EA3 over RT. Now you can easily compare. This is of the form A into E power minus EA over RT, right? So in the place of A, what you have? So here, when you compare these two equations, this one with this, I mean this equation with this equation, what you have is, in the place of A, you have A1 into A2 square by A3. So this is the overall Arrhenius parameter or overall frequency factor of the reaction. And what is overall activation energy? So here, minus EA is equal to minus EA1 minus 2EA2 plus EA3, right? I'm just comparing these two terms, okay? So here overall EA is equal to minus EA1 minus EA2 plus EA3. Now I'll take this minus on this side, or on the both sides I'll multiply it with minus sign. It becomes EA is equal to EA1 plus 2EA2 minus EA3. So this is the expression for overall activation energy. Now you have expression for overall frequency factor and overall activation energy. So in this question we did nothing. We just substituted this rate constants with these terms in the Arrhenius equation. So then we just separated these rate constants and exponential terms, and then we compared this with normal Arrhenius equation. We got this overall Arrhenius parameter and overall activation energy. Okay. So this is how we solve this problem. Let's move on to the next problem. Let's solve the 8th question now. So the question is, the rate constants of a reaction at 500 Kelvin and 700 Kelvin are 0.02 second inverse and 0.07 second inverse respectively. Calculate activation energy and Arrhenius parameter. So here you are given two temperatures and two rate constants, and you are asked to find the value of activation energy and Arrhenius parameter. So what is T1? One temperature is 500 Kelvin and the rate constant at 500 Kelvin is 0.02 second inverse. Okay. And other temperature T2 is 700 Kelvin and the rate constant at that temperature is 0.07 second inverse. Okay. So you have two temperatures, two rate constants. Using this equation, you can easily find activation energy. Okay. First we will find activation energy and then we will see how we can find Arrhenius parameter. Okay. So let's start. So the equation equation is log K2 by K1. Write it here. Log. I'll just substitute the values. K2 is 0.07 by K1 is 0.02. So this will be second inverse. This also will be second inverse. So second inverse and second inverse will get cancelled. So there is no point in writing. So this is just a number. Okay, we have to find EA, and in the denominator we have 2.303 into R. So what is R? 8.314. What are its units? Joule, Kelvin inverse and mole inverse, right? Yeah, Joule, Kelvin inverse, mole inverse. Now we have two temperatures. What is T2? T2 is 700 Kelvin minus 500 Kelvin. So I will just write it as 700 minus 500 into Kelvin. Okay. In the denominator we have T1 into T2. That means 700 into, or I can write it as 700 Kelvin into 500 Kelvin. So Kelvin into Kelvin will be Kelvin square. So here I can cancel 1 Kelvin. Actually this K should be capital K, okay? So this capital K represents Kelvin and small k represents rate constant. So I am making a mistake here, but you please don't make these mistakes. This is capital K, not small k. So this capital K represents the unit of temperature and this small k represents rate constant. So I am cancelling 1 Kelvin here. So what you have is, you just have a Kelvin in the denominator. Okay. So what can we do? Okay, I will have to find activation energy. For that I need to take this entire term on the right hand side. Okay. So this denominator will go to the numerator when I take it to the left hand side. Okay. So here, first let us solve this. I can take this as 7 by 2 because it is 0.07, 0.02. So 7 by 2 is 3.5. So this becomes log of 3.5. So log of 3.5 into, now I will take this to numerator. 2.303 into 8.314 joule Kelvin inverse per mole into 700 into 500. You have 1 Kelvin here. Kelvin. Okay. Divided by, so what is there in the numerator will go to the denominator. So this is 700 minus 500, which is 200. So I will write 200 in the denominator. There is no unit here, so I have written nothing. So let us first try to cancel the units. So here I can cancel Kelvin and Kelvin inverse. So the unit that you have is joules per mole. So that is the unit of energy, right? So activation energy is expressed in joules per mole. When you solve all these terms, the answer you get is, yeah, this log 3.5 is 0.5440. So using calculator, when you solve this, you will get 18,228.0791 joules per mole. Okay. So this is the value of your activation energy. Now we have activation energy. We need to find the Arrhenius parameter. How do we do that? So when you look at this equation, in this equation we have A. So to find the value of A, we should know rate constant, we should know temperature, we should know activation energy. So we have found activation energy. Now we have one rate constant, we also have temperature, right? You can use either these two values to find A, or you can also use these two values. Okay, the answer will be same. So I am going to use the temperature as 500 Kelvin in this equation and its corresponding rate constant as 0.02 second inverse. So I am putting these two values and activation energy in this equation to get the value of A. You can also put these two values. Okay, so the answer will be same. So what we have, K is 0.02 second inverse. But okay, before this let us do one thing. Let us first solve this EA by RT, okay? And then directly put the value of EA by RT in this equation. So what is EA? So let us find EA over RT. Its value is 18228.0791 joules per mole, okay? Divided by, what is the value of R? R is 8.314 joule Kelvin inverse mole inverse. And mind you one thing, when you are doing this EA by RT, this R and EA should be in same terms, I mean same units. If you are expressing R in joules, your activation energy should also be in joules. It should not be in kilojoules, okay? Okay, so temperature is 500 Kelvin. So I'll cancel Kelvin inverse, Kelvin here, mole inverse with mole inverse, joule with joule. So EA over RT is just a number. So when you solve this using calculator, the value you get is 4.3849. So I had already solved this, it is 4.3849. I am just going to put this value in this equation. So now what we have K as 0.02. I am putting the value of K 0.02 is equal to A into e power minus EA over RT. So minus EA over RT will be minus 4.3849. So the value of e power minus 4.3849 is 0.0124. So when you solve it using calculator, you will get this as 0.0124. So A will be 0.02 divided by 0.0124. So the answer will be somewhere around 1.6129. So this is the value of Arrhenius parameter. Sorry. So you had find the value of activation energy and Arrhenius parameter. So this question was very simple. You are given two temperatures, two rate constants. So you had used this Arrhenius equation to get the value of activation energy. Now you have activation energy. You know one rate constant. You know one temperature. So you can easily get the value of Arrhenius parameter. Okay. So now let us move on to solve the ninth question. The ninth question is the first order rate constant for the decomposition of ethyl iodide by the reaction. So this is the given reaction, and the first order rate constant at 600 Kelvin is this much, 1.60 into 10 power minus 5 second inverse. Its EA, activation energy, is 209 kilojoules per mole. Calculate the rate constant of the reaction at 700 Kelvin. So you are given the rate constant at 600 Kelvin. You are asked to find the value of rate constant at 700 Kelvin. You are also given the activation energy. By the way, this what is this reaction? So this is alkyl halide. So alkyl halide is converting into alkene, and this is hydrogen halide. So this is an example of dehydrohalogenation reaction. Okay. So let's move to the question. So what is given? One temperature is given, which is 600 Kelvin, and the rate constant at this temperature K1 is 1.60 into 10 power minus 5 second inverse. So we have one temperature, one rate constant. We have one more temperature, T2 is given. We are asked to find the value of rate constant at 700 Kelvin. So we are given the activation energy, which is 209 kilojoules per mole. Okay. So you have two temperatures, you have one rate constant, you have activation energy. You need to find the value of other rate constant. So for that you can use this equation, right? So you have rate constant, one rate constant, activation energy and two temperatures. So you can easily use this equation and find the value of K2. So I am substituting all these values in this equation. Let me write it here. Log K2, we don't have the value of K2, we have to find it by, we have the value of K1 as 1.60 into 10 power minus 5, which is equal to EA 209 kilojoules per mole by 2.303 into R. So what is R? 8.314 joule Kelvin inverse mole inverse. Now notice one thing here. So the numerator is in the unit of kilojoules and denominator is in the unit of joules. So when you are using this, the value of R as 8.314, you need to represent this activation energy in the form of joules. Okay. You can do either way. You can represent this in the form of kilojoules or you can represent it as joules. Okay. But both the numerator and denominator should be in same units. Okay. So what I will do is I will express this kilojoules as joules. So we know that 1 kilojoule is equal to 1000 joules. So I will just multiply the numerator with 1000. So this becomes 209 into 1000 joules per mole. So now both the numerator and denominator have same units, joule and joule. Okay. So what is T2? T2 is 700, T1 is 600. So 700 minus 600. So 700 Kelvin minus 600 Kelvin. I will write Kelvin outside by 700 Kelvin into 600 Kelvin. So Kelvin into Kelvin will become Kelvin square. So here I can cancel 1 Kelvin. So what I am left with is 1 Kelvin in the denominator. Okay. So this will be 100, right? So this will be 100. 700 minus 600 will be 100. And this will become 7 6 are 42. 42 into 1, 2, 3, 4. 4 zeros. So I can cancel these 2 zeros. Now you have. So here I can also cancel these 2 zeros with 1000. So you have 2090 divided by. So let us first cancel the units. Here joule will be cancelled with joule. Mole inverse will be cancelled with mole inverse, Kelvin inverse and Kelvin. Okay. So this will be 2090 by 2.303 into 8.314 into 42. Okay. So this value comes out to be, so I have already solved this. This comes out to be 2.5989. Please check it. Okay. This will be 2.5989. So here log K2 by 1.60 into 10 power minus 5 is this much. 2.5989 is 2.5989. So we know one formula, that is log A by B is equal to log A minus log B. So this is of the form log A by B. I can write it as log A minus log B, right? So I will write this as log K2 minus log 1.60 into 10 power minus 5, which is equal to 2.5989. Okay. So now when you look at this term, this is of the form log A into B. So log A into B can be written as log A plus log B. So I am going to use this mathematical formula here. So that becomes log K2 minus log 1.60. So I'll put this in bracket, plus log 10 power minus 5, which is equal to 5989. Okay. So we have one more mathematical formula, that is log a power n is equal to m into log a. Okay. So when you have log a to the power n, you can bring this n here, n into, it becomes m into log a. So this will become log 10 power minus 5 will be minus 5 into log 10, right? So this will become minus 5 log 10. And we know that log 10, which is to the base 10, is equal to 1, right? So this log 10 will be 1. So this is what we have. So now when I multiply this minus with the terms in the bracket, this will become minus log 1.60 plus 5. Okay. What can I do now? So this log 1.60 is 0.20411. Okay. So this is log K2 is equal to, value of log 1.60 is 0.20411. So this will be 0.20411 into 5, which is equal to 2.5989. So here it is. So this becomes 4.79589. So 5 plus this value becomes 4.79589. So I'll write it here. This will be 4.79589. Okay. So now we have, where do I write? I'll write it here. We'll have log K2 is equal to 2.5989 minus 4.79589. 2.5989 minus 4.79589. 79589. So this will be log K2 is equal to, this will be minus 2.19699. Minus 2.19699. So this K2 will be 10 power minus 2.19699. Right? If we have log K2 is equal to A, then K2 will be 10 power A, right? So this is the formula. So this is the logarithm, this is antilog. So you have log on the left hand side, I took the antilog, so that becomes K2 is equal to 10 power. So this log is to the base 10. So this becomes 10 power minus 2.19699. So the value of K2 is 10 power minus 2.19699. So when you solve this using calculator, you will get K2 as, it will be 0.006353. 0.006353. So this is your value of K2. So K2 is what? K2 is rate constant, and that too it is a first order rate constant. So the unit of a first order rate constant is always second inverse, right? And you can also write this as K2 is equal to 6.3. I'll write it here. K2 can also be written as 6.35 into 10 power minus 3 second inverse, right? I have just multiplied and divided it with 1000. Okay, so it becomes 6.3 into 10 power minus 3 second inverse. So this is the rate constant at 700 Kelvin. So I hope this class was useful. Thank you so much. See you in the next class.